Lagrange interpolation functions. So Lagrange interpolation functions are also just a simple way of setting up the shape functions. If you would like to know more mathematical details about Lagrange interpolation functions, how do they arise, then I would recommend you to look into a standard book on numerical analysis or basically linear algebra. It will give you much more information, but because in the finite element analysis I only want to make use of the Lagrange interpolation function to make our life easier, I will only give you information based on that. It's a very useful tool if you want to set up shape functions or formulate shape functions for higher order elements. Because as I said, if you have higher order elements and you want to form the shape functions and you want to do it by the standard way by setting up the approximation order and then substituting the boundary conditions back into it and then solving for the unknown number of constants in the equation, then you can get a very large system of equations which might be difficult or where it takes very long to solve. So instead of going through that complicated process, so we can use Lagrange interpolation functions to form our shape functions. In this approach, we can represent shape functions by product of linear polynomials instead of a higher order polynomial. So for example, if I have a polynomial of order n minus 1, okay, so we say we pick a polynomial of order n minus 1 to be equal to the approximate behavior function, then we can write the shape function ni, which could be any shape function, to be equal to the product of, so this pi basically means product of, it's just like summation but instead of sum, product of m is equal to 1 to n of x minus, so linear function x minus xm, so of course x here changes from 1 to n, so you use a function product of this divided by a product of xi minus xm, where m of course changes from 1 to n and I is the current node or current degree of freedom identity. However, you omit at each time in both numerator and denominator x minus xi and xi minus xi. So in the denominator you omit xi minus xi, of course you're going to get 0, so infinite, and in the numerator you will omit x minus xi. So let's take as an example a cubic polynomial. So we say we have a cubic polynomial to represent a certain element. It could be any element, I'm not going to specify what kind of element it is, I just say I'm taking a cubic polynomial. Then in that case ue is equal to c1 plus c2x plus c3x square plus c4x cubed. So that's a cubic polynomial. And if we want to use the definition of the shape function by means of Lagrange interpolation functions, then I can write S1 to be equal to, it's a product of x minus xm excluding x minus xi as given over here. So I can write x minus, of course x1, 1 is the first one, so m is equal to 1, 2, 4 in this case because you have c1, c2, c3, c4. So then I will omit x1, so I will start with x minus x2, x minus x3, x minus x4 divided by x1 minus x2, x1 minus x3, x1 minus x4. So I know in this case that x1 minus, so if I take for an example, yeah, let me just pick up an example now because then I can put numbers and show you the final shape function or S1. If I say again that it's a, just a simple one-dimensional element which is axial, that means only 1 degree of freedom per node, then if I use a cubic polynomial, I am introducing 2 extra nodes along its length. So if I say this is 1, 2, 3 and 4, Then I have S1 is equal to, as I have described here in terms of x and x2, x3, x4. Now if the total length of this element was L, then each element when divided equally in length is given as L by 3. So now we know the definition, so we can substitute it here. So I will have x minus x by 2, x minus x by 3, sorry, x minus x4, not by, divided by x minus x1 minus x2 is equal to minus L by 3, also in terms of direction. x1 minus x3 is equal to minus 2L by 3, and x1 minus x4 is equal to minus L. So if I put all this together, I will get minus 9 by 2L cubed, x minus x2, x minus x3, x minus x4 as my final shape function for degree of freedom 1. And in the same way, I can formulate the shape function for every single node. You can of course work this out yourself, but it's a very simple tool which you can use for very complex shape function formulation just by using a product of linear functions.